Hello, my name is Korpan, and today I'll be presenting VBMO, voting-based, multi-objective path planning. Nowadays, autonomous agents must consider multiple planning objectives as they navigate to their destinations in complex real-world environments. Some of these objectives might include minimizing the distance traveled, maintaining the maximum amount of safety, or minimizing travel through crowds. In the past, and honestly today as well, many navigators use single objective path planning, oftentimes minimizing distance. But multi-objective path planning is an important area of research because people and robots need to consider multiple objectives as they navigate through the world. For example, if you have a robot that may be navigating through a warehouse, it may want to minimize the distance it travels while also avoiding congestion and pursuing the most efficient route of the objects it needs to pick up. Now, how has this been done before? Well, people have used things like weighted sums, where you weight each of the objectives and then use a single objective approach, or meta-heuristics like evolutionary methods. Others have tried things like NAMOA star or MHA star, which modifies the search process itself to try to balance the different objectives on each step of the planning process. Furthermore, others have reduced this to a two-objective or bi-objective problem. Here I present VBMO, voting-based multi-objective path planning, where the algorithm tries to find consensus among multiple objectives and is guaranteed to produce a Pareto optimal plan. The thesis of this work is that voting provides a more efficient way to balance multiple objectives. So let's start with some definitions. In single objective planning, a planner minimizes an objective beta in a graph G to produce a plan P sub beta. This plan is optimal if no other plan has a lower total cost. So here we're minimizing our objective beta. In multi-objective planning, we have a set of objectives, B, which are the objectives beta 1 to beta j, and each of the plans can be evaluated with these objectives, so beta of P. So on the top right, I have an example with two objectives, beta 1 and beta 2, and we could have two plans, P1, which does well on beta 1, it's minimizing beta 1, and P2, which does well on beta 2. Well, in this space of how well plans conform to these two objectives, we could create many such plans that all exist on this spectrum of doing well on beta 1 and beta 2. We call one plan dominating another plan when that plan is scored as less than or equal to for every beta, but strictly less than for one beta. So for example, the red plan here is dominated by P5. And in fact, all of these blue points here are plans that are dominated solutions. We call the set of non-dominant plans the Pareto frontier. So the goal in multi-objective planning is to find plans on the Pareto frontier. Unlike single objective planning, where you can have a single plan that is optimal, multi-objective planning, you have now a set of plans and you have to choose among them the ones that are along the frontier. So VBMO is relying on the fact that in the multi-objective context, the graph, the underlying graph is the same. So here we have a graph G, the vertices are unobstructed locations in that environment, and we can create edges between adjacent unimpeded nodes. and we apply a cost to those edge that represents the cost of movement between the two nodes based on whatever our objective is. We can use graph search algorithm like A star, and we label the edge with the cost for each objective. So here, if the objective is to minimize distance, we can use Euclidean distance between the two nodes to represent the cost to travel between them. And so what this means is, if we have another objective, the graph is still the same, right? The nodes, the vertices, the edges, only the edge weights differ. So here in this graph on the right side, you can see S is the start vertex, T is the target vertex. If our objective is to minimize distance, we could produce a plan like this, the purple colored line. If we have another objective, which is to maximize travel through these pink areas, perhaps areas that are highly safe to travel through, well, we could have a different set of edge costs and produce a different plan as a result. So here's an example of a map from a benchmark, one of the benchmark environments we use for evaluation. And given this map, we can produce a graph, and then we can assign edge weights to this graph based on different objectives. So if our objective is to minimize the number of steps, we could apply a uniform cost, which is the first one you see on the left. If we're minimizing distance, here the colors represent green for lower cost, red for higher cost, so the diagonals are longer than the for horizontal or vertical edges. Here is an example of a random set of edge costs, here from 1 to 20. And then lastly, safety avoids areas where there's limited travel. So wherever the degree of vertices is lower, safety assigns a higher cost of travel. Now, VBMO's algorithm first starts by finding an optimal plan, PJ, for each objective J. It then scores that plan on how well it conforms to each of the other objectives. These scores are in the range of 0 to 1. And it selects the plan with voting. Now here we have 3 different voting mechanisms. Range voting will pick the plan with minimum total cost. Borda voting uses ranking. So we take the scores, we rank them, and then we pick the plan with maximum total points based on the rank. The last one is combined approval voting. It assigns a value of -1 to plans that do not conform to an objective maximally, 1 to those that maximally conform to that objective, and 0 to the plans that are in between. And so it will then select the plan with the maximum total value. Any ties are broken in. So let's look at an example of this. Excuse me. With 6 objectives, beta 1 to beta 6, and 6 plans, P1 to P6. Each objective produces a single plan, but then you can evaluate that on the other objectives. So here, for example, P1 has a score of 0 for beta 1, meaning it is optimal for beta 1, but it's not necessarily optimal for the other objectives. The scores are normalized for an objective from 0 to 1. So for example, with beta 1, P1 does best on beta 1, P4 does the worst. Now we can apply this to all the plans for all the objectives. And if we're doing range voting, we can take the total score here and select P2 as the plan with minimum total score. With Borda voting, we use the rankings. And given the rankings, we pick the one that has maximum total points. And in this case, that's actually P3. And combined approval voting selects P1. So the different voting mechanisms find different types of consensus among the objectives to select the plan that best adheres to those objectives. So here's an example from that same environment I showed you earlier. Here we have, again, distance, uniform, and safety, along with random. And VBMO will select safety here as the plan that does best on safety, but does pretty well on the other objectives. This was evaluated in comparison with an equally weighted sum of the objectives, and then using a single objective approach on a set of diverse benchmark environments, 156 environments from Dragon Age Origins. These ranged from small environments with only 168 nodes to those with 137,000 nodes. It was also evaluated in the DMAX New York City road network, which has many more nodes, 365,000, but with a smaller average degree. Here are some examples of environments from the Dragon Age set that have different types of configurations and sizes. Here, the heuristic used was Euclidean distance for the Dragon Age Origins environments and Haversine distance for DMAX. Results were averaged over 50 randomly selected start and target vertices, and significance was measured at 0.05. The first experiment looked at 3 objectives and compared the 3 voting mechanisms. The objectives were distance, a random value of 1 to 20, and a uniform value of 1. And in this case, VBMO both scored significantly better with all 3 voting mechanisms and was significantly faster with all 3 voting mechanisms. When we look at the specific plan that was selected, right, it will only select a plan that is optimal in a single objective, but does pretty well in the others. In all 3, distance was most often the plan that was selected. Well, the second experiment wanted to compare, again with 3 objectives, but why don't make it with its equal magnitude? And the reason to do that is because in the first experiment, the random objective had a range of 1 to 20. Well, the weighted comparison that we're making here weights all 3 objectives equally. So with a objective that has the ability to have a much larger magnitude, can overwhelm the distance and uniform objectives when they're equally weighted. So here, this experiment is to give all 3 objectives an equal footing so that the weighted single objective planner has a chance. And in this experiment, VBMO actually performed significantly worse in terms of its score. However, it was still significantly faster than weighted. The third experiment wanted to look at whether randomness was having an effect here. And so it took out the random objective and replaced it with the safety objective. And it found here that VBMO with range voting scored significantly better in the majority of the environments, and it was significantly faster. The fourth experiment looked at the New York City roadmap environment, and it compared different sets of objectives. First, it looked at 3 objectives. DMAX comes with 2 objectives built in, distance and time. And here I added a third one, uniform cost across all edges. Well, with a small uniform cost of 10, there was no significant difference in terms of the score. But when you made the uniform cost 2,000, so that it was about equal magnitude of distance and time, weighted was scored significantly better. In both cases, however, VBMO was significantly faster. Third was with 4 objectives now, including a random objective. And in this case, VBMO scored significantly better. And the last 2, well, I looked at the data set further and found that distance and time were 96% correlated. And so I took out time because VBMO is comparing objectives performance on other plans. And if distance and time are highly correlated, a plan that does well on distance will also do really well on time. So here we use distance, uniform, and a random objective, and VBMO does significantly better in terms of score and time. So just to conclude, VBMO is a fast, flexible, and scalable multi-objective path planning approach that generates plans on the Pareto frontier. Currently, we're examining additional environments and objectives, looking at other voting mechanisms and alternative graph search algorithms and heuristics. Future work will evaluate this with a hybrid evolutionary approach, iterative optimization of weights. Thank you so much for listening, and I look forward to your questions.